Greetings to all the respected panel members and my dear fellow attendees of this session. My name is Sanket Salvi and I am here to present my paper on the topic LiCamIoT, an 8x8 LED matrix pattern to camera communication for Li-Fi IoT based applications. My name is Sanket Salvi. I am one of the co-authors of this paper along with my guide, Dr. Geetha V. We are from the Department of Information Technology, National Institute of Technology, Karnataka. This is the presentation outline where we'll discuss about what was the motivation behind this particular topic, its related work, the entire details of the proposed system, its requirement analysis, implementation, experimental setups, result, and conclusion. Coming to the introduction. The Internet of Things has paved the way for creating new intelligent applications. Here, things imply any physical entity that can sense the environment, generate information, and be capable of communication across the network using Internet. IoT applications can be classified based on their deployment environments. For example, agricultural, healthcare based, roads, industries, etc. It is predicted that IoT uh, will highly influence the next industrial revolution. It implies that more smart devices will connect to the network. Most smart devices connected to the network use radio frequency. However, increasing the number of the devices using shared channels also increases the complexity of spectrum allocation and multiplexing, leading to the spectrum saturation. Therefore, the visible light spectrum usage for short distance communication between devices is one of the solutions to reduce radio frequency saturation. Techniques such as visible light communication, Li-Fi, that is light fidelity, and optical camera communication use the visible light spectrum to achieve this task. In optical camera communication, at the transmitter side, the information to be sent is modulated using light features such as light intensity, colors, blinking frequency, or patterns. On the receiver side, camera captures these changes in features and the system performs demodulation to reconstruct the sent data. If the transmitted data is sensor related, which can be stored for monitoring and provide information related to the deployed environment, then an IoT system using OCC, that is optical camera communication, can be built. The advantage of such system could be its non-reliance on radio frequency spectrum and reusability of existing hardware such as LED and camera. With a motivation to build such a system, this paper proposes a novel 8x8 LED pattern for camera communication technique. The objectives of the proposed system are as follows. To design a QR code inspired 8x8 pattern for ease of detection and rotation compensation. To communicate sensor data using the proposed frame format and pattern mapping. To evaluate the system performance based on the SNR, distance, PER, and packet rate. These works have inspired us for carrying out the work in this domain and has helped us to identify the problem statement as well as provided sufficient details in order to understand the system in much more clarity and depth. The system used these systems yeah these systems used distributed MIMO topology and which helped us in understanding the scope of Li-Fi IoT integration and its range of applications. These works inspired the building of Li-Fi system that can be integrated within IoT architecture to achieve required application objectives. And these systems have provided insight into the required processes involved for our proposed system and its evaluation metrics. Coming to the overall architecture. The proposed architecture of LiCamIoT is as shown in this figure. The system is divided into two parts, that is transmitter and receiver, separated by free space optical communication channel. The left part of the figure shows various industry machines with inbuilt sensors. The reading from these sensors will be converted to an 8x8 LED pattern based on the proposed frame format. Each machine can be identified using the unique ID pattern. Assuming that the industrial area is under CCTV surveillance, a camera will capture frames from the environment as per its field of view, including the LED matrix. The captured image will undergo image preprocessing for ROI extraction, that is region of interest extraction, and the extracted ROI will be rotated if needed to fit the bounding box. Finally, the rotated image will be cropped and resized to an 8x8 matrix for pattern matching and decoding. The decoded bits will be combined to reconstruct the transmitted data. The complete process detail is mentioned in the upcoming slides. Anchor points. So as you can see here, this is the frame format that we are using for projecting the sensor data, where you have three 3x3 matrices. Such we have four 3x3 matrices at the four corners. These four corners are also called as the anchor patterns. The orange colored one is called as the sensor type pattern, which means it will give you the information about, it will give the system about the information of a sensor. And the pink one is this will indicate the sensor value, the exact value of what it has sensed will be defined by the pink section. Although this entire thing looks colored, this is just for ease of understanding. The actual pattern would be only using red LEDs, and the pattern will be decoded based on this particular format. The corner 3x3 patterns are used to identify the orientation of the transmitter, and based on the alignment, the captured image will be rotated or will undergo rotation in order to align it properly and then decode the correct values from each section. The frame format of the proposed system is as shown in figure 3. The 28-bit frame is divided into three subframes. Sensor type and fragment number are 6-bit subframes that will provide the type of the sensor and current fragment number respectively. The fragment number subframe will be used for sensor values that require more than 16 bits for representation. The number of necessary fragments will be fixed as per sensor type. The final 16-bit subframe will provide sensor value. The fragments will be merged in case of fragmented data to give the absolute sensor value. Coming to the decoding process. On the receiver side, a continuous video will be captured at a low frame rate. Image frames will be separated from the video, and each image frame will undergo pre-processing as shown in this figure. The input colored image first will get converted into grayscale. The grayscale image will be converted into binary. That binary image will then be dilated, and the largest white blob will be extracted from that image. That largest blob will then be cropped across the bounding boxes. If it is matching, in order to check whether it is matching or it has captured the entire area properly or not, we will perform a hue transform on it and then keep on rotating such that the ratio of the bounding box and the actual captured area is minimum. Then we will resize the 8x8 binary value that we have obtained. We will match the patterns, the 3x3 patterns that we have seen in the previous slide. We'll match those patterns, and based on that we will extract the sensor type, extract the fragment number, and finally extract the values to provide the entire format, entire packet together. These are the matrices that we are going to use in order to evaluate. That is the SNR for of our system, the power, that is uh, um, the difference of pixel values uh, between the image when it is sending data and with respect to the image which does not have a transmitter which is sending data. So those two images will be compared with each other in order to obtain the SNR. We'll also use PR, that is packet error ratio, in order to evaluate the system, which is nothing but a ratio of the erroneous packets received out of the total packets sent. The requirements of these particular in order to implement the proposed system are as follows. We can see we have one temperature sensor, that is DHT11. We have one Arduino Uno, which is a programmable board, an LED array, and a webcam for the receiver side. The implemented hardware looks like this, where we have attached the 8x8 LED matrix to the Arduino Uno. We have also connected the temperature sensor to Arduino Uno so that the temperature sensed from the DHT sensor will be converted into its corresponding 8x8 pattern. To show the receiver side, we have a camera on the left corner where which will be capturing these frames and decoding it frame by frame. The system to which the camera is connected has these configuration, as well as this was the preset camera parameters that we have provided based on few earlier preliminary experiments that we have conducted. The first experiment that we have conducted was to check the validity of the implemented system. And to do that, the receiver and the transmitter were kept at 50 centimeter distance from each other, and a real-time data from DHT11 sensor was transmitted using the proposed pattern communication technique. The ambient light intensity was recorded up to 5 to 10 lux, which is very low. Uh, that was the light intensity of the environment when the experiment was conducted. The processed binary matrix was successfully decoded to provide 100% reconstruction. That means the entire pattern was properly reconstructed for 8x8 binary matrix, and the transmitted pattern was successfully received on the receiver side. So this image shows two frames. Frame 1 is having 32 as the data, and frame 2 is having zero point 0.4 as the data represented. The sensor type here is temperature, which requires two frames, that is 32 bits, in order to send the entire value, or in order to send the particular sensor value, and that's why it requires two frames. That's why you can also see on the left side of the image, the frame number is 1 and the value is 32, while on the right side in image the frame number is 2, that is the second frame for the same data, and the value received is zero point 0.4. So overall the temperature here is 32.4 degrees Celsius. The second experiment was conducted to observe the impact of distance on LED light intensity and blurring. In order to note this, we have plotted intensity profiles for various distances, and it was observed that as the distance increases, the intensities of these lights get spreaded, and that's why it causes difficulty in order to decode a particular pattern after a certain distance. The third experiment was conducted to measure the SNR. SNR was measured at various distances, for example, at 50 centimeter and 100 centimeter distance. And at these distances, we found out that SNR value continuously decreases as the distance increases. That is for uh, when the light intensity, ambient light intensity was low, the SNR value was comparatively better as compared to the when the ambient light intensity was slightly higher. This is majorly because as the difference between the background noise, that is when the ambient light intensity is very low and when the transmitter is on, the difference between these two frames will be very high when the light intensity is low. But as the light intensity increases, the difference between the transmitted signal and the received signal, or the because of the background noise, becomes very less. The figure here shows how we have carried out the SNR measurement. On the right side, that is figure 9, shows the results of SNR versus distance versus ambient light intensity, and how it is continuously decreasing with the increase in the distance as well as with the increase in the ambient light intensity. Uh, Larger the SNR, better would be the quality of this particular signal. In the final experiment, we evaluated the packet error ratio with respect to 2000 packets. The number of the error packets were noted and the percentage was calculated. Figure 10 shows the increase in PR with the increase in distance. That means the errors were increasing as the distance was increased. It was also observed that with an increase in packet rate, the PR also increased. Coming to the final conclusion, the proposed system was built with the motivation to offload the RF spectrum and use visible light spectrum for IoT communication. An optical camera communication, that is OCC based Li-Fi IoT system, was implemented using 8x8 LED matrix and a camera. The real-time temperature and humidity data were successfully transmitted over the distance of 2 meters using the proposed system. The performance of the proposed system was evaluated using SNR, PER, packet rate at various distances, and ambient light condition. LiCamIoT showcases the future of IoT and Li-Fi integration in an indoor environment. These are the references used for implementing this work. Thank you.